Dear and beloved students, welcome to our class on solar radiation. This is the second chapter of our course Agrometeorology and Climate Change. Now, before I actually start the class, until all our students enter and then take their seats, I just would like to tell a small story. It is a very simple one. How some boys were playing near a pond. They saw a number of frogs in the water, and began to pelt them with stones. They killed several of them. After a while, one of the frogs, lifting his head out of the water, cried out at the boys, "I pray, I pray, I pray. Stop, stop, stop. My boys, I pray, stop pelting stones on us. What is sport to you is death to us." The moral is, one man's pleasure may be another man's pain. Okay, now, so let us go into the class. Today, as I said in the beginning of this class, we are going to discuss the second chapter of our course, that is solar radiation. Solar radiation is the primary source of energy on the earth, and life depends on it. The solar radiation is defined as the flux of radiant energy from the sun. The flux of radiant energy from the sun, meaning the energy coming from the sun, is known as solar radiation. In the universe, there are three major ways of transmission of energy. In the scientific parlance, we call them as processes of transmission of energy. Otherwise, transmission of energy is heat. Okay, heat energy is transmitted by three processes. 1, radiation; 2, conduction; 3, convection. 1 minute back I told solar radiation is defined as the flux of radiant energy from the sun. Now, while explaining the first one, I take this definition only: the processes of transmission of energy. 1, radiation. This is the process of transmission of energy from one body to another without the aid of a material medium. There is no material medium in it, neither solid nor liquid, anything. Therefore, radiation is the process of transmission of energy from one body to another without the aid of a material medium. Example is the energy transmission through space from the sun to the earth. Okay. The second process of transmission of energy is conduction. The process of heat transfer through matter without the actual movement of the molecules of the substances or matter is known as conduction. Once again, I would like to repeat, the process of heat transfer through matter without the actual movement of molecules of the substances or matter is known as conduction. Heat flows from the warmer to cooler part of any body so that the temperature between them are equalized. Until the temperatures are equalized, the heat flows from warmer to cooler part of the body. Now, an example for conduction is the energy transmission through an iron rod which is made warmer at one end. When we make an iron rod warmer at one end, the energy transmits until the temperature between 2 points are equalized. This is known as conduction. Here there is no actual movement of the molecules of the medium. Now the third one is the convection. This is the process of transmission of heat through actual movement of the molecules of the medium. This is the process of transmission of heat through actual movement of molecules of the medium. This is the predominant form of transmission of energy on the earth, as all the weather related processes involve this process. So, once again, for explanation, I would like to impress upon you, convection is the process of transmission of heat through actual movement of the molecules of the medium. In the conduction, actual movement of the molecules or substances is not there. Here in the convection, there is a actual movement of the molecules of the medium. An example is boiling of water in a beaker. Boiling of water in a beaker. Now, after trying to understand what is solar radiation and what are the processes of transmission of energy, from your examination point of view, maybe in midterm for 2 marks or maybe 3 marks, this question would come. What is that? Explain in brief the processes of transmission of energy. Yes, so that you can write these three. Now, the second part of our solar radiation basics 1 class is importance of solar radiation on crop plants. From germination of seed to harvesting and even post-harvest processes are affected by solar radiation. Second, solar radiation provides energy for all the phenomena related to biomass production, all photosynthetic processes and all physical processes taking place in the soil, the plant and their environment. Another most important point of importance of solar radiation on crop plants is solar radiation controls the distribution of temperature, thereby the distribution of crops into different regions. This is a very simple and interesting point in the importance of solar radiation on the crop plants, that is, the distribution of temperature is controlled by solar radiation, thereby solar radiation controls the distribution of crops into different regions through distribution of temperature. Now, so far in our class, we tried to understand what is the definition of solar radiation, what are the processes of transmission of energy or radiation, conduction, convection, and importance of solar radiation on the crop plants. Now, there are some basic laws of solar radiation. These basic laws are fundamentally physical laws. Okay, very simple but very interesting. Practically, enormous advantage is there for the basic radiation laws. Number one, just wavelength. The wavelength of electromagnetic radiation is given by a small equation, mu is equal to C by V, where or delta, okay, is equal to C by mu. Okay, right, that's also correct. The wavelength of the electromagnetic radiation is given by delta is equal to C by V, where the delta or lambda is equal to wavelength, the shortest distance between consecutive crests in the wave trance. That's what we call it as. C is the velocity of light. You are very well aware, 3 into 10 to the power of 10 centimeters per second. Mu is the frequency. Now, so the wavelength is a very interesting, smallest of the definitions that you may have studied in the physics of 8th, 9th, 10th classes, and even in the intermediate as well in physics. Now, the second one is Planck's law. The electromagnetic radiation energy content E of each quantum is proportional to the frequency given by the equation. The electromagnetic radiation energy content E, capital E, is H mu. E is equal to H mu, where H is Planck's constant, 6.625 into 10 to the power of minus 27 x per second. Mu is the frequency. The law states that greater the frequency, greater is the energy of the quantum. Now, the third one is Kirchhoff's law. A good absorber of radiation is a good emitter. In similar circumstances, this law states that the absorptivity A, small a, of an object for radiation of a specific wavelength is equal to its emissivity, small e, for the same wavelength. The equation of the law is A lambda is equal to E lambda. In the wavelength also, lambda is equal to C by mu. Similarly, in Kirchhoff's law, A lambda is equal to E lambda. Now, Stefan-Boltzmann law. The intensity of radiation emitted by a radiating body is directly proportional to fourth power of the absolute temperature of that body. It's a very interesting definition coined by Stefan-Boltzmann. Stefan-Boltzmann law states that the intensity of radiation emitted by a radiating body is directly proportional to the fourth power of the absolute temperature of that particular body. Flux is equal to sigma T to the power of 4, where T is equal to 273 plus degree centigrade, because the temperature is in kelvins. Stefan-Boltzmann constant is 5.67 into 10 to the power of minus 5 earths per centimeter square per second for degree Kelvin to the power of minus 4. So, this is Stefan-Boltzmann law, and the Wien's displacement law is the next one. The wavelength of the maximum intensity of emission from a radiating black body is inversely proportional to its absolute temperature for your benefit. It's a very interesting, very simple law. The wavelength of the maximum intensity of emission from a radiating black body is inversely proportional to its absolute temperature. For small example or explanation, if the temperature of a body is high, radiation maximum is displaced towards the shorter wavelengths. For the surface temperature of, say for example, 5793 degrees Kelvin, evaluated for the sun, lambda maximum is 0.5. The most intense solar radiation occurs in the blue-green range of the visible light. The wavelength of maximum intensity of radiation for the Earth's actual surface temperature of 14 degrees centigrade or 287 degrees Kelvin is about 10 microns, which is into infrared band. This is what I would like to discuss with you. Basic radiation law, simple wavelength, what you have studied in your basic courses of intermediate. Then Planck's law, Kirchhoff's law, Stefan-Boltzmann law, Wien's displacement law. Thank you. We meet in our next class on solar radiation in the